This talk is about two papers. The first one is the QuDit ZH calculus, generalized Toffoli+Hadamard, and universality. It's joint work with Patrick Roy, John van de Wetering, and myself. And the second paper is exact synthesis of multi-Qutrit Clifford cyclotomic circuits. It's joint work with Andrew Glottal, Neil J. Ross, John van de Wetering. And first, just in case anyone wants to talk to me about other research topics for today or tomorrow, I'm currently a fourth-year PhD, so just finished my fourth-year PhD of student at the University of Oxford, and I've got one more year left, so I'll think about and I'm looking to apply to what to do after PhD. These are the main areas I research. In my PhD, I would like to thank Google for funding my a PhD fellowship to fund my PhD. And I also work half-time as a research engineer at Continuum in the Oxford office. And I'm also on a multi-institutional quantum education project that's at Oxford, Continuum, IBM, and some other universities as well. Here's the talk outline. So first I'll talk about intro to qudit gates, as well as introducing the qudit Toffoli+Hadamard gate set for prime-dimensional qudits. Then intro to quantum graphical calculi, specifically qudit ZX and ZH calculi. Then universality of the new qudit ZH calculus, and then exact circuit synthesis results. First about Qutrit gates in the Clifford hierarchy and prime-dimensional qudit gates. First of all, courtesy of, well, you've seen this a lot. These 2 days is, here's a generic Qutrit state and some overview of Qutrits. You can have physical or non-physical systems with dimension greater than 2. Qutrit is a special case of d = 3. So you can't simulate qudits using qubits efficiently, for the most part, and it's kind of interesting because you can already play with qudits on today's kind of, even if they're called qubit devices, most qubit devices actually do have higher levels. So we saw a lot of talks this conference about superconducting qudits. So for example, if you've got a nonlinear oscillator potential and you've just got these higher levels, and you kind of just ignore the higher levels when you are looking at qubits, but then the higher levels are just there and you can use them for computation too. Many people believe that quantum computers must be fault-tolerant to be useful. Not everyone, but and the Cliffords, well, in a Heisenberg-Weyl Cliffords, generalize to prime-dimensional qudits and to continuous variable systems. These are efficiently classically simulable, but they're not universal for quantum computation. So you have to add at least one non-Clifford resource in order to have universal quantum computation. For these qudit polys, let's let omega be the dth root of unity, where d is the qudit dimension. And you have the clock and shift poly x and z operators. You also have such that qubit x and z, their matrices look like this, as you're familiar. And for Qutrits, they'll look like this. And you can kind of see that the pattern would generalize for any qudit dimension x and z, not necessarily prime. So but for just prime-dimensional qudit Cliffords, you have that doing x and z d times is identity, that you can do a discrete Fourier transform. So that's also called the Hadamard gate, although strictly it's not a Hadamard matrix. You also have the Weyl-Brading relations when you commute x and z past each other, getting a phase of omega. And you have the notion of Clifford hierarchy. So whenever you commute a gate in the nth level of the Clifford hierarchy with a poly, then the correction is going to be in the n-1th level of the Clifford hierarchy. So notably, the first level of the Clifford hierarchy then is the polys, the second, the Cliffords, and the third, the most famous example is the T gate. So qubit Cliffords, I might use qubit for prime-dimensional qudits, although it's not the best sounding name. SH and CX gates will generate them. So it is a group. And I'll use this notation for CX because there's different kinds of CX gates. This is the Clifford CX gate, or also called the C-sum gate, where this lambda control is just doing the control, does the target unitary to the power of the control. So that's just a convention. So QuDit generalizations of X and CX gates are not necessarily Pauli or Clifford. For example, these two, just for Qutrits, these two Pauli X gates, like X+1 and X-1 mod 3, are Pauli. And these three are Clifford. So this is the gates that say exchange ket 0 and 1, but does identity on the ket 2 state, for example. And if you go to even higher dimensions, you'll get single qubit permutation gates that are non-Clifford. So even these things, even though physically they're easy to implement, they can be, or even if you can readily implement them physically, there isn't a way to do them fault tolerantly without invoking a lot non-Clifford resources. Yeah. So for example, even the Qutrit case, this ket 2 controlled Pauli X gate is already non-Clifford. And coming back to this, the kinds of non-Clifford gates that you can add, it's best if they can support magic state distillation and injection. So the most popular example, this is the Qutrit+T gate. And this is the Qutrit+R gate. So although it's got only ones and zeros and minus ones in the matrix, but it's actually non-Clifford. The T gate is in the third level of the Clifford hierarchy, and the R gate is nowhere in the Clifford hierarchy. And kind of where this all started, I think the first paper I worked on in this area was to show that Clifford+R is a strict subset of the Qutrit Clifford+T gate set. So even though with just third level Clifford hierarchy gates, you can still exactly do a single Qutrit non-Clifford gate that's nowhere in the Clifford hierarchy. In this talk, these two papers, we also further realized, okay, in the middle, there's actually this gate set called, which we call Qutrit Toffoli+Hadamard. So you can add non-Clifford qudit gates, and more generally, there is a paper on diagonal gates in the qudit hierarchy by Gottsman. And then for the T gate, you can generalize to prime dimensions, as they've done here. In the third level of the Clifford hierarchy for all prime dimensional qudits. And you can also have a different generalization of the Qutrit+T gate to any prime dimensions. So I call this the dth root of Z gate, and it's now in the dth level of the Clifford hierarchy. But the kind of interesting thing is that the T gate, on the left, we don't know how to build qudit dit string controlled Toffolies, so from which you can build all the other Toffolies using Clifford+T for any dimension higher than 3, versus this dth root of Z gate, we do know how to build it. So yeah, it is costlier to be at a higher level of the Clifford hierarchy, but it's still conjectured to be fault tolerant, or you can still do gate teleportation with it. And in Qutrits, these coincide because they're generalizations of it. About the qudit Toffoli+Hadamard gate set we can now get to. So you can actually define different things to be called the Toffoli and justify it. The kind of most obvious definition is let's do another lambda control on the lambda controlled X, also known as the Clifford CX gate. So this corresponds to multiplication mod D for D qudit dimension. A different definition, and the one we came up with before, we also explored the other one, was ket 0 controlled Pauli X gate. So it's ket 0 controlled. So if your control is in the ket 0 basis state, then you do the target Pauli X gate. Otherwise, you do identity on the target. And we also realized that you can show that these are equivalent gate sets up to a Balrog and Scylla. So it's justifiable to call these legitimate Toffolies in the sense that just like how for qubit Toffoli, you can generate all of the binary classical reversible gates. Now for prime dimensions, odd prime dimensions, you can, with either of these, no matter which you choose, you can get all of the d-ary classical reversible gates and Scylla free. So You can also build the Ket0 controlled gate in terms of the Clifford+D root of Z gate set. So no, the construction is kind of interesting. It comes from a Microsoft paper for Qutrit, but then I realized it also works for any prime dimension. And the kind of trick is that you can just do a small calculation and then put a Clifford global phase on the control. So, so in short, this gives us a way to do fault tolerant, or conceivably fault tolerant, and there's a lot more ingredients to fault tolerance, but conceivably fault tolerant Toffoli gates exactly in higher dimensions, which previously wasn't known. So for Qutrit, that was our paper here. And before that, all the people had constructed Qutrit Toffolis. They used like Ancilla that had to be in the Ket0 state, or non-fault tolerant gates operations such as Gibbons rotations, or qubit gates pairwise on Qutrit states, or gate counts that were exponential. So having a polynomial gate count, and later we can get it to linear gate count as well, was, I think, an improvement and quite fun. So the linear gate count construction just looks really cool because on the left-hand side, you have from Gidney the qubit version for linear gate count, decomposition of arbitrary size Toffoli in terms of smallest Toffolis. And it turns out this also works for QuDits, even though it was quite non-obvious. You can then use that previous construction. Once you have any dit string controlled Toffolis, then you can build any QuDit classical reversible circuit. You can exchange any two dit strings. So here, this is the circuit to do so, using these dit string controlled Toffolis. And once you can do that, then you just have like an exponential number of these, and then you can build any d-ary classical reversible function. It's necessarily exponential gate count, but we checked this is within a log n, where n is the number of qubits, a factor of the minimum gate count that would be necessary just by counting argument. So in addition, once you've got this Ket0 controlled X gate, which generates all the classical reversible gates, then you can, and you also need the X gate, but that's you can just plug in a Ket0 or something. If you add to it just one gate, the Hadamard gate, then you get a approximately universal gate set. It's interesting how in the qudit, odd prime dimensional qudit case, this is a stronger result than in the qubit case. In the qubit case, you get something that's computationally approximately universal, so you can simulate any universal quantum computation with qubits, but you don't actually implement the unitary directly, versus here you can. So just this we can now justifiably call this a Toffoli+Hadamard gate set, because it is approximately universal, and your Ket0 controlled X gate is a suitable 2 Qutrit or 2 qudit version of the Toffoli. It's interesting, it doesn't have an analog in the qubit case, because in the qubit case you don't have any 2 qubit equivalent of Toffoli, because all of the 2 qubit classical gates are Cliffords. So it's quite interesting. And here is my favorite part of the talk. Most of my PhD research is on quantum graphical calculi, so we'll speed run this. But basically, you can think of them as kind of undirected graphs with two types of nodes, or like tensor networks, where special types of nodes that are specifically designed to correspond to the Z and X observables. So their definitions in bracket are on the bottom. So the green or Z spider is in the diagonal in the Z basis, and the X spider is diagonal in the X basis. And just this, where you have phase labels of just e to the I alpha for some real valued alpha angles, that's enough to give you any linear map on any number of qubits. So you can prove any equalities of qubit linear maps using just these 8 rules on this slide here. So if there exist 2 diagrams that are equal, mathematically equal, then you can there will always exist a series of these rewrite rules that you can kind of substitute into parts of the diagrams, such that you get the proof. that they're equal using just rules of the calculus. So essentially, you're kind of replacing, instead of using some symbolic or other modes of or matrices or other modes of computation, you just entirely have the diagrams be mathematically faithful to the underlying computation. And ZX calculus is kind of more suitable for kind of a Clifford plus phases gate set, such as Clifford+T or Clifford plus, or Cliffords, or depending on which fragments you're looking at. And since 2023, I'm kind of fast forwarding a lot because, like, okay, from here to here is like 1 decade, and then from here to here is another 5 years. But you can prove any equalities of any finite dimensional Hilbert space linear maps using just a finite number of rules. So this is past year, over the past year and a half, like we now have completeness of just quantum graphical languages for all of finite dimensional Hilbert spaces. So any mixed dimensional computations as well. Of course, saying that there exists a proof doesn't necessarily mean it's easy to find one. And generically, you'll have an exponential time process to find one in the general case, which is kind of unavoidable due to complexity reasons. But at least you guarantee that you're not looking for some proof that doesn't exist, that you're not missing any rules. So I kind of just dumped onto this slide here a bunch of applications. Quantum error correction should really be here, but I had trouble kind of picking a figure for it because there was quite a few papers on it. But there's lots of things you can do. Oh, I should pause on this a bit longer. So now we can go over a bit of intro qubit ZX calculus just to get a taste of it. But just what it looks like, if you you can convert from the circuit model to ZX calculus quite easily for most operations. You just have to sometimes figure out which kind of calculus you want to use that's the best fit. So for the basic qubit ZX calculus, it translates in this way. Your green and red are like that. Also, this also works if you horizontally reflect, that is doing in this case, taking the bra instead of taking the qets. So, yeah, those are the bra 0, 1, plus and minus. And for single qubit gates, here are your green and red, 1 input, 1 output spiders, and they're exactly the z and x rotation gates of angle alpha about the z-axis of the Bloch sphere and x-axis of the Bloch sphere, respectively. You have a fusion rule, which says that if you have got 2 spiders that are connected by at least 1 leg, and these 2 spiders are the same color, you just fuse them and you add their edges together. You add their angles together. So in this case, having no label is angle 0, and then so 0 plus pi is pi. So you could just smush them together. For multi-qudit ZX calculus, you have a 1 input, 2 output green spider copies states in the computational basis. And a 2 input, 1 output red, so X spider, adds states in the computational basis. So you can then have your CX gate literally just connect these 2 things, and that's your CX gate. So here I've shown the proof for qubits, but it's the same proof, except you have to kind of be careful of the edge direction for QuDits. You can also choose a variation of the calculus where you don't have to care about the edge direction, but then you get some of the rules become a bit more complicated. It's kind of choose your own adventure. So the CX gate if you have the target be the QuDit+ state, like here, so this is the QuDit+ state plugged into the target of the CX gate, you can first do a copy rule, because the red spider copies basis states that are green. So you can just copy it, and then you can fuse. You can also do that with the QuDit- state input into the target of the CX gate. This also works if you plug in QuDit0 to control and QuDit1 to the control, respectively. So it's kind of cool that you can have this symmetry. And so that's kind of a good example we use in our teaching high school students, for example. As we're also about teaching high school students, I thought I had to show this because this is University of Waterloo, and this is some master students' notes on quantum teleportation in a course here. And so we got permission from her to use these notes to compare it to the equivalent ZX calculus proof. So using just these two rules on this slide, that if you have an x rotation or z rotation of angle 0, it's identity. And then if you just the normal spider fusion rules for z and x, you can teach quantum teleportation with pictures using no matrices or complex numbers or tensor products. So this is the circuit just translated from the circuit to ZX calculus, one gate or operation at a time. And here's the proof. It basically fuses the spiders together, and then you bend the wires because only conductivity matters, and then remove all the identities, and you get just that quantum teleportation. You get whatever Alice is state with, it goes to Bob. So that's it's quite satisfying. So I'm kind of skipping quite a bit of definitions here, but just to get a taste of what it looks like. For prime dimensional qudits, we have Clifford completeness, which means that if you have any Clifford computations, you can have a simplified calculus that always lets you prove inequalities of linear maps which are Clifford. For qubits, it looks like this. So it's all of the qubit ZX calculus rules minus the one that is non-Clifford. And for QuDits, for prime dimensional qudits, the rules actually look almost the same, which is not surprising, but it's kind of satisfying that it's very concise. And we were able to do the generalization. And kind of recently more satisfying, we can also generalize to infinite dimensional, so continuous variable case, which, although it's known you can Heisenberg Weyl that, but you can also get non-Clifford stuff with this generalization as well. Now to Toffoli+Hadamard gate set. So you can draw any quantum circuit that could be post-selected in the Toffoli+Hadamard gate set using the phase-free ZH calculus on the left side here. It's like the ZH calculus, except instead of x, you use h. So instead of graphs, it corresponds to like hypergraphs if you were to write them back in the ZX calculus. So this now can let you, since Toffoli+Hadamard is approximately universal, you can now approximate any linear map on any number of qubits to arbitrary low error for QuDits. And you can also, for qubit Toffoli+Hadamard, you just need these 8 rules here. For QuDits, we came up with the definition of the qudit H box. So this square, it's like a generalization of Hadamard to have multiple legs defined here. We kind of looked at Qutrit phase gadgets, and we thought this is likely a form that we should try, and it did work out. But you can think of it as a calculus for arithmetic in ZD. So where the X spider gives you addition on computational basis states, and then the H box here gives you multiplication, if you kind of follow this H box with the Hadamard dagger. Multiplication mod D of computational basis states. So then you can use H boxes, a generalization of that, where you now have a label that is an element of a ring, some ring, whatever ring you choose. And much note that both Z and H are flexometric for QuDits, so we chose it such that you can bend the wires whichever way, and only the conductivity matters of your graphs. So here's some of the basic rules. I didn't show the more complicated ones, but these ones will look familiar to people from graphical calculi. But basically, you've got 2 types of fusion rules, and then you got fusion rules for Z and H, and then you've also got a bialgebra rule, which basically, like the top one is like that addition and copying are distribute with respect to each other, and then the bottom one is that copying and multiplication distribute with respect to each other, for example. So here, those 2 versions of qudit Toffoli that I showed earlier, we can draw them in the ZH calculus like this, respectively. And it's nice because now you've got a symmetric drawing, a way to represent CZ, which more than drawing is correct, and you can just apply the color change rule about this green. So like you can consume these Hadamards when you change the color of this red spider to get the green. So just like in qubit case, if you conjugate one of the controls of the CCZ gate, any of them, by Hadamards, you get a CCX gate where that one's the target. So also have these like CCZ magic states. So the H-box, the three-legged H-box, is just if you plug the 3 plus states into the CCZ gate. And we use this trick as well as quite a few other tricks to translate any QDit ZH calculus diagram to the QDit ZX calculus, plus the trick of decomposing the Toffoli's further into Clifford plus d-ary of z, which is a single QDit phase gate. For the universality proof of the calculus, also known as showing that you can express anything in the calculus, you can express any linear maps that are in this fragment of computation in the calculus. So for arbitrary rings, we do a Schur product of matrices over these rings. And since you can write any of these matrices as a Schur product of some matrices that are pseudo-binary, what we call super-binary, which means all the entries are either 1 or r. R could be 0, for example, or just anything in the ring. Then we write it as a logical formula with a polynomial that corresponds exactly to that logical formula, and then we just implement the polynomial with a diagram of this form, where we can inductively build a bigger and bigger polynomial based off the polynomial of one size smaller with one less variable. And David, who's here in the audience, yeah, he's waving, has done some follow-up work on this that's really great. That is generalizing this to arbitrary finite fields, ZH calculus, yeah. So universality of phase-free ZH calculus, continuing that proof, you can also for the phase-free case where you don't have access to these boxes, like with arbitrary r's, you only have the default one without a label, which just means phase omega. So where omega is the d-ary of unity. Now you have to build successor gadgets to get all of the integers. And to get all these natural numbers, we use this trick of you build Pascal's triangle. So this is Pascal's triangle as a lower triangular matrix. And then you can build, with the polynomial trick on the previous slide, build a ZH diagram which has a multiplexer. And then you just recursively build each row of Pascal's triangle by applying this gate R, this map R, where you also build R with the polynomial trick on the previous slide. And then you get this successor gadget, which sends the H-box of any label to the H-box of that label plus 1. Then, because the phase-free H-box gives you the label omega, then this gives you H-boxes for all the elements in the ring Z omega, which is the ring that corresponds to Toffoli+Hadamard. So now one question is, what can you build out of the Toffoli+Hadamard gate set? So the question of exact synthesis is the problem of if you've got a circuit, what is the ring that corresponds to all circuits in this gate set? So in the nice cases, then there's a bijective equivalence between these two. So it's easy to look at all gates in a gate set and see, do all the matrix elements, are they within some ring? But how do you know you've chosen the smallest possible ring? And moreover, that any unitary matrix in this ring gives you, can be built by some circuit in this gate set. So the opposite direction is the hard one that usually requires an algorithm called an exact synthesis algorithm. So to solve the problem, usually you're figuring out this red arrow, because the green arrow is easy. So a primer on some basic number theories that would be needed is that rings are like, you've got two binary operations over addition and multiplication. You can extend a ring by adding a new number to it. And you can localize a ring by adding new denominators to it. And maybe people who are watching on YouTube can like pause and look at it longer. So here I will also just, there's quite a bit of literature review, I guess. I will just kind of flash it up here, but again, maybe better for the YouTube people. So for qubit exact synthesis, these two are the two single qubit Clifford+T papers. And this is the multi-qubit Clifford+T paper for exact synthesis. So this is D extended by omega ring is the ring corresponding to qubit Clifford+T. For Qutrits, this is the single Qutrit exact synthesis papers. And this is the ring for any Qutrit, sorry, this is the single Qutrit Clifford+T papers. And this is the ring for single Qutrit, or just any Qutrit, for any Qutrit polys. This is for Qutrit Cliffords, and this is for Qutrit Clifford+T. So all the matrix elements are in these rings. For exact synthesis, we need to show the other direction for this algorithm. And so for Clifford+T, we can actually use a trick where we can inject circuits that are made out of Clifford+T. We can kind of do almost all of it using Toffoli+Hadamard gates, and then just use some resource states to get the matrix elements that are outside of the Toffoli+Hadamard ring, but inside the Clifford+T ring. So the T gate, or this kind of generalized single Qutrit T sub k gate is this. And the Clifford cyclotomic gate set is an infinite hierarchy of gate sets defined by this, which is the Toffoli plus H plus this T sub k gate. For the lowest level of this hierarchy, it's Toffoli+Hadamard, and for the second lowest, it's Clifford+T. So we use catalytic embeddings, which is a brand new technique from the past year. Basically, you've got a unitary U. That is the one you actually want to do, and then you've got phi of U, which is the one that you do in the one gate set below that in the hierarchy, and with this catalyst magic state C, which is called catalyst because you don't consume this magic state, but you need it to do computations that are outside of the ring that you would have if you didn't have the catalyst. So you can do a series of these catalytic embeddings. That's how, using our Toffoli+Hadamard exact synthesis, we're able to get all of the Clifford cyclotomic gate sets by just successively doing catalytic embeddings until you've gotten to the lowest level of the hierarchy. So yeah, I think I'm out of time. So but yeah, but this is like the good stopping point because it's the main technique for doing the catalytic embeddings. And I'll give a talk next week at the Quantum Physics and Logic conference more about this paper, where I would be able to cover the proof technique as well. Thank you, everyone.